Welcome to Math Zone African Motives. Today, we're diving into a crucial topic in calculus and physics, kinematics. In this tutorial, you will learn to calculate velocity and acceleration using derivatives and to describe the motion of objects using these concepts. Specifically, by the end of this video, you will be able to 1. Understand and apply the definitions of displacement, velocity, and acceleration. And 2. Use calculus to find velocity and acceleration from a position function, both for straight line and circular motion. Let's get started. First, let's establish the fundamental concepts and the formulas we'll be using throughout this tutorial. We'll begin with rectilinear motion, which describes movement in a straight line. Imagine a particle moving back and forth on a straight line, like a car on a road. The first key term we need is displacement, denoted by the letter S. Displacement is the change in the position of an object. Its unit is usually meters or any unit of distance. It's a vector, meaning it has both magnitude and direction. It's not the same as total distance traveled. Next is velocity, represented by v. Velocity is defined as the rate of change of displacement. This is a crucial link to calculus. Velocity is the first derivative of the displacement function with respect to time. It tells you how fast an object is moving and in which direction. So we write the formula as v equals ds dt, where ds dt represents the derivative. Finally, we have acceleration, denoted by a. Acceleration is the rate of change of velocity. Similar to velocity, acceleration is the first derivative of the velocity function. Because velocity is already the first derivative of displacement, acceleration is the second derivative of displacement. The formula for acceleration is a equals dv dt, or alternatively, a equals the second derivative of s with respect to t, written as d squared s over dt squared. Let's summarize. If you have a function for displacement s of t, you can find the velocity by differentiating it once. Differentiate again, and you have the acceleration. To recap, displacement is the change in position. Velocity is the rate of change of displacement. And acceleration is the rate of change of velocity. These are the fundamental building blocks of rectilinear kinematics. Now let's explore circular motion. This is comparable to rectilinear motion, but the movement is around a circle. Instead of a linear displacement, we talk about angular displacement. Angular displacement, symbolized by the Greek letter theta, represents the angle through which an object has rotated from its initial position. The standard unit for angular displacement is the radian. If we have a position function theta of t, we can find the rates of change just as we did before. The rate of change of angular displacement is called angular velocity, represented by the Greek letter omega. Just like velocity is the derivative of displacement, angular velocity is the first derivative of the angular displacement function. And the rate of change of angular velocity is angular acceleration, represented by the Greek letter alpha. Angular acceleration is the first derivative of angular velocity, or the second derivative of angular displacement. A common convention is to take the counterclockwise direction as positive. These formulas are identical in structure to the rectilinear formulas. We are simply applying the same calculus concepts to a different type of motion. So, to recap circular motion, angular displacement theta becomes angular velocity omega when you differentiate it once, and angular acceleration alpha when you differentiate it twice. We've covered the theory. Now let's put it into practice with our first example. We'll be working through example 338 from your textbook. Take a moment to read the question carefully. Pause the video and try to solve it on your own first. Okay, let's solve it together. We are given the function for angular displacement, theta equals 50t minus 5t squared. This means that for any time t, we can find the wheel's angular position. Our first goal is to calculate the angular velocity at t equals 4 seconds. To find velocity, we need to differentiate the displacement function. Remember the formula. Angular velocity is the derivative of angular displacement. So we need to find the derivative of 50t minus 5t squared. Using the power rule for derivatives, the derivative of 50t is 50, and the derivative of 5t squared is 5 times 2t, which is 10t. This gives us our angular velocity function, omega equals 50 minus 10t. This equation tells us the velocity at any time t. The question asks for the velocity specifically at t equals 4 seconds. So we substitute 4 into our velocity equation. That's 50 minus 40, which equals 10 radians per second. This is our final answer for part 1. So, at 4 seconds, the wheel is rotating at 10 radians per second in the positive or counterclockwise direction. Now for part 2, we need to find the angular acceleration at t equals 4 seconds. Acceleration is the derivative of velocity. We'll differentiate the velocity function we just found. We need the derivative of 50 minus 10t. The derivative of a constant like 50 is 0, and the derivative of negative 10t is negative 10. Our acceleration function is alpha equals negative 10 radians per second squared. Notice that there is no t in this equation. This means the acceleration is constant regardless of time. So, even though the question asks for the acceleration at t equals 4 seconds, the acceleration is always negative 10 radians per second squared. This negative sign indicates that the acceleration is in the opposite direction of the positive convention, meaning it's accelerating clockwise, slowing the wheel down if it's spinning counterclockwise. Let's verify our answers. The memo also gets 10 rads and 10 rad s too, so we are correct. That was a great first example. Now let's try a more complex problem involving rectilinear motion. In this next example, the position of a particle is given by the function s of t equals t cubed minus 6t squared plus 9t. Our first task is to find a formula for the velocity at any time t. Let's list our given information. The position function is s equals t cubed minus 6t squared plus 9t. Our objective is to find the velocity v of t. We know the relationship. Velocity is the derivative of position. So we need to differentiate to cubed minus 6t squared plus 9t. Using the power rule again, the derivative of t cubed is 3t squared. The derivative of 6t squared is 12t, and the derivative of 9t is 9. Therefore, our velocity function is v equals 3t squared minus 12t plus 9. This equation will be useful for the remaining parts of this problem. Excellent. We have successfully found the general formula for the particle's velocity. Let's move on to the next part of this question. Next, we're asked to find the velocity specifically at time t equals 2 seconds. This is a direct application of the velocity function we just found. We'll use our velocity formula, v equals 3t squared minus 12t plus 9. Now, we substitute t equals 2 seconds into the formula. Calculating this, we get 3 times 4, which is 12, minus 24 plus 9. This simplifies to negative 3. So the velocity at 2 seconds is negative 3 meters per second. The negative sign is very important. It tells us that the particle is moving backward, or to the left, at that exact moment. Let's quickly check our work with the provided solution. It matches. Verified. We're continuing with example 334. We've found the velocity function and the velocity at t at d2. The next part asks a very common question. When is the particle at rest? Think about what at rest means. An object at rest is not moving. And what measures how an object is moving? That's right, its velocity is 0. So, to find out when the particle is at rest, we need to find the time t when the velocity is equal to 0. We'll take our velocity function, v equals 3t squared minus 12t plus 9, and set it equal to 0. This is a quadratic equation. Let's solve it for t. We can simplify it by dividing the entire equation by 3. That gives us t squared minus 4t plus 3 equals 0. This quadratic can be factored. We need two numbers that multiply to 3 and add up to negative 4. Those numbers are negative 1 and negative 3. So we factor it into t minus 1 times t minus 3 equals 0. For the product of two terms to be 0, at least one of them must be 0. This gives us two possible times. T equals 1 second and t equals 3 seconds. These are the moments when the particle is momentarily at rest before changing direction. Let's check the memo. It confirms our answer. Verified. Now for the most visually interesting part of this problem. We're going to graph the position, velocity, and acceleration functions together. Graphing helps us understand the relationship between these three functions and how they describe the motion. We've already done most of the work. Let's start with the position function. Position is s equals t cubed minus 6t squared plus 9t. We found the intercepts by setting s at 0, which gave us t0 and t3. We also found the moments of rest, ty1 and t3, by setting the derivative to 0. These moments correspond to the maximum and minimum points on the position graph. We calculate the position at these times. At t1, sesha 4, at t3, sesha 0. These are our turning points. Now let's plot the graph of the position function. It starts at 0 zeros, goes up to a peak at 1000 force, comes back down to the t-axis at 3000, and then climbs upwards. This is the ft curve on your graph. Next, the velocity function, vi of t, was 3t squared minus 12t plus 9. We know it's a parabola. Crucially, we know that velocity is 0 at t1 and t3. So this parabola must cross the t-axis at those points. This corresponds to the gt curve. Notice how it's 0 exactly where the position graph has its peaks and valleys. Finally, acceleration. Acceleration is the derivative of velocity. We differentiate 3t squared minus 12t plus 9. This gives us the linear function a equals 6t minus 12. This straight line is the ht curve. We can see its relationship to the other two graphs. Let's summarize the graph relationships. The slope of the position graph gives you the value of the velocity. When the position graph is going up, its slope is positive, and the velocity graph is above the axis. When the position graph is flat, its slope is 0, and the velocity graph is on the axis. The same applies to the velocity and acceleration graphs. Let's use our graphs to understand the particle's motion. Remember our results from example 334. We found velocity is positive for t between 0 and 1, negative between 1 and 3, and positive again for t greater than 3. This means the particle is moving forward for the first second, then backward for 2 seconds, and then forward again. This changing direction is key to understanding the total distance traveled. Let's calculate the total distance covered in the first 5 seconds. To find total distance, we must sum the absolute values of the distances covered in each segment of motion. First, the particle moves from t0 to t1. The distance is the absolute value of the position at t of t1 minus the position at t of t0. That's the absolute value of 4 minus 0, which is 4 meters. This corresponds to the distance moved to the right. Next, it moves from t1 to t3. The distance is the absolute value of the position at t3 minus the position at t1. That's the absolute value of 0 minus 4, which is also 4 meters. This is the distance moved to the left. Finally, from t3 to t5, we need to find the position at t5. Substituting t5 into our position function gives s equals 20 meters. So the distance covered in this segment is the absolute value of 20 minus 0, which is 20 meters. This is the distance moved to the right again. The total distance is the sum of these three distances. 4 plus 4 plus 20 equals 28 meters. This is the actual path length the particle traveled. This is a key takeaway. Total distance is the sum of all path lengths. Displacement is just the straight line distance from the start to the end. In this case, the total distance was 28 meters, but the displacement from t0 to t5 was just s of 5 minus s0, which is 20 meters. By breaking the motion into segments where the velocity sign was constant, we were able to calculate the correct total distance. Our result matches the memo. Verified. Let's work through one more comprehensive example, this time involving trigonometric functions. The position of a particle is given by s equals 2 times the quantity 1 plus cosine squared t. Calculate the velocity when t equals pi over 4. Our first task is to calculate the velocity at t equals pi over 4. Again, velocity is the derivative of position. To differentiate this, we'll need the chain rule. So we differentiate the outer function, which is 2 times something squared, and multiply by the derivative of the inner function, which is cosine t. Let u equal cosine t, so s equals 2 times the quantity 1 plus u squared. The derivative of 1 plus u squared is 2u. The derivative of u, or cosine t, is negative sine at. Combining these, we get 4u times negative sine t. Substituting u back in, our velocity function is v equals negative 4 cosine t sine t. Now we evaluate this at t equals pi over 4. Remember, pi over 4 radians is 45 degrees. The cosine and sine of pi over 4 are both the square root of 2 over 2. Substituting these values, we get negative 4 times root 2 over 2 times root 2 over 2, which simplifies to negative 2 meters per second. The memo shows an alternative method using the double angle identity, but it arrives at the same answer. Our result is verified. Continuing with our trigonometric example, we now have a velocity function. The question is, when is the velocity 0? Just like before, at rest means velocity equals 0. So we set our velocity function to 0. We have -4 cosine t sine at equals 0. This equation is true if either cosine t is 0 or sine t is 0. On the unit circle, cosine t is the x-coordinate and sine t is the y-coordinate. Let's consider the interval 0 to pi over 2, which is the first quadrant. Within this interval, cosine t is 0 only at t equals pi over 2, and sine t is 0 only at t equals 0. So the velocity is 0 at 2 times, at equals 0 and t equals pi over 2. The question asks for the position s at these times. Let's use our original position function to find s for each of these t values. At t equals 0, s equals 2 times 1 plus cosine squared of 0. Cosine of 0 is 1, so this is 2 times 2, which is 4 meters. At t equals pi over 2, s equals 2 times 1 plus cosine squared of pi over 2. Cosine of pi over 2 is 0, so this is 2 times 1, which is 2 meters. So when the velocity is 0, the position of the particle is either 4 meters or 2 meters. The memo confirms our findings. Verified. Let's finish this problem by finding the acceleration at a specific time. We are asked for the acceleration at t equals pi over 2. Acceleration is the derivative of velocity. We'll differentiate our velocity function equals -4 cosine t sine t. This requires the product rule. However, a simpler way is to first rewrite the velocity function using a trigonometric identity. Recall the double angle identity for sine. 2 sine at cosine t equals sine of 2t. We can rewrite v as -2 times 2 sine at cosine t, which is simply -2 sine of 2t. This is much easier to differentiate. Now, acceleration is the derivative of this simplified velocity. We use the chain rule again. The derivative of sine of 2t is 2 cosine of 2t. Multiplying by the -2, we get our acceleration function. A equals -4 cosine of 2t. Finally, we evaluate this at t equals pi over 2. 2 times pi over 2 is pi. Cosine of pi is -1. So A equals -4 times -1, which is positive 4 meters per second squared. The positive sign means the acceleration at that moment is in the positive direction. And just like before, our answer is verified by the memo. Let's quickly recap what we've learned today. We started with the core concepts of kinematics. We saw how displacement, velocity, and acceleration are related through differentiation. We applied this to both rectilinear and circular motion, using both polynomials and trigonometric functions to describe position. We learned how to find the velocity and acceleration at any time by taking the first and second derivatives of the position function. And crucially, we saw how setting velocity to 0 can tell us when a particle is at rest or changes direction, which is essential for calculating total distance traveled. By understanding the relationships between position, velocity, and acceleration, you can now fully describe and predict the motion of an object. Thank you for watching this tutorial from Math Zone African Motives. If you found this video helpful, please subscribe for more tutorials.